Hello everyone. My name is Jason from Essex BCI Group from University of Essex, UK. And first of all, nice to meet you all, and I really appreciate having this opportunity to talk about my research. So today, I'm going to talk about classifying Siren-sound mental rehearsal and Covert production versus idle state for onset detection, or BCI. So this is conference. Introduction, methodology, results will be discussed, followed by question and answer. And this is necessity of the research. Throughout the years, BCIs have been categorized in several different ways: invasive versus non-invasive, and spontaneous versus event-related. However, today, here I would like to talk about synchronous versus asynchronous, which is queue-based and self-paced systems. So most of the current BCI systems, such as P300 and SSVP or some auto imagery, fall into queue-based system category. And as you can see from the figure, the queue-based system on the bottom of the figure, user sends a command when the machine allows it. So the machine let the user know when to start and when to stop, and user must follow the timing. However, in the self-paced system, user just send the command whenever they want to, and the machine listens all the times, and it is more intuitive and natural to the users. And this is comparison table between self-paced and queue-based system. So queue-based system is normally simple to design, and data labeling is quite easy because they know when is the active state and resting period. So due to this, it normally has better classification rate. However, there is one big issue with usability. If you imagine that you are controlling a wheelchair in a busy road, and the control timing is chosen by the machine, but it will be really difficult to control and as well as dangerous. So if we move on to the self-paced system, it is more complex to design and difficult data labeling, but it is more natural and intuitive to control. However, there is an issue with this system as well, which is onset detection problem. Onset detection is detecting when a relevant message is sent by the user, and it should be able to classify the active task from idle or resting period. And this is what I'm researching and what I'm going to talk about today. And this onset detection problem should be solved before the self-paced BCI can be used in real-world situation. And this is goal of the experiment. And the goal of this experiment was using Covert Siren-sound production for onset detection by classifying this task from idle state. And the experiment is yet moved to online situation, so it was designed with self-queue-based offline system, which I'm going to talk about later on. So the main goal of this research is investigating the new potential method for onset detection in BCI. So, and there is an ultimate goal for the future world. So if this system developed further, it can be used like a Google Now. So like this, if you just say, okay Google, it doesn't recognize. Okay Google. Yeah, you can activate your machine by saying just, okay Google, and you can comment it later on. So if this system develops further, you can activate your machine with your thumb and with your brain signal. And it can be implemented very simple on and off paradigm, as well as some queue-based BCI system. Any other kind of queue-based BCI system can be worked as like a self-paced system with this onset detection. So this is task and idle state definition. So in terms of active state, covert Siren-sound production was used. Covert sound production is different from our normal speech in overtree. And it doesn't actually make sound out, but think of think of making it, as well as auditory recall, which is imagination of hearing the sound. So for example, participants were instructed to make siren sound in this experiment. And during the imagination of re-syllable, they were instructed to imagine high pitch, and during u, low pitch. So like a re or for a couple of seconds. And they were not allowed to imagine tone or mouth or any other body movement to reduce motor imagery related signals. And in terms of idle state, and this would be equivalent to non-state and non-specific task. In some literature, they recorded idle state with closed eyes, but this alpha wave generation, they regarded the alpha wave generation state as an idle, but in real world, it cannot be like that. So in this experiment, we just recorded idle state with eyes open, but they allowed to blink their eyes. So this figure shows the recording procedure for one trial, and there were two different protocols. Protocol A is marker followed by task, and protocol B is task first and then marker. Both commonly, the category Q shows either up and arrow and X randomly at the beginning of the trial, and it indicates siren sound, active task, and idle state, respectively. And it presented on a screen for 2 seconds, and it disappeared to reduce class-dependent visual event-related potential. So after that, in the protocol A, the participants just press a key whenever they're ready, and they execute their task, and either the siren sound or idle state. And the stop cue appears on the screen, and the one trial is finished. However, in the protocol B, the participant just execute the task first, and then press the key for marker. And for the marker, the same key was pressed all the time to eliminate class-dependent information related to the motor task of pushing the different keys. So there were 5 subjects, and it was recorded with 64 channels and 1 reference channels. And the sample rate was 256. At the signal processing part, 3 different window lengths were investigated, 1, 2, and 3 seconds. And it was bandpass filter with referencing, which is subtracting yellow channel. So for the feature extraction, wavelet transform was used for the feature extraction, and the wavelet packet decomposition was applied to the pre-processed EEG data, and it was decomposed up to level 5. And all the 64 channels were featured individually and used as an input of classifier. Then the best node and best channel were determined from the classification result. And as you may already know, using different wavelengths can make big difference in classification rate. So 3 different wavelengths were tested in this experiment, the DB2 and Whole-Flat2 and Signal2. So for the classification part, linear support vector machine was used with 24 validation to increase reliability. And this is result. The classification accuracy from the best channel and the best node with an appropriate wavelength was around 79%, average of 5 subjects. And compared to protocol A and B, the protocol B gave better classification result for most participants, which is quite promising us, as this protocol is more similar with cell-based system, that people execute their task without any cue or marker. And in terms of window size, the difference were insignificant. The Wilcox test p-value was above 0.05. Thus, the 1 second window can be regarded the most efficient window length, as it reduced the computational power as well as increasing the system speed. So the red circle represents the best channel, and the best channel that gave highest result, classification result, and it is distributed all around the head, not only broadcast and monicus area. And it shows that covert siren-sound production brain activity appears all around the head. due to volume conduction problem. So physiological information of siren-sound production is difficult to identify, but classification visual tells it is distinguishable and it is quite promising toward onset detection in BCIs. And so for the future work, it will be moved to online situation and it will be tested in outside lab setting. And adaptive learning will be applied to reduce false positive during the idle state. And this is photo of BCI group in University of Essex, which is one of the leading group in UK. And I thank all of them, especially to my supervisors, Francisco Sepulveda, who's in front. And this is the end of the presentation. Thank you very much.
Okay, my question is, if you do this cyber verification, can you say something about the underlying physiology that you expect? Is there suppression of a rhythm or something that is going on?
You mean the physiological location?
Not the location, I think it's clear, but is this oscillatory thing that you expect?
We expected the broadcast and monicast area, which is related to vocalization and word processing part. We expected that part, but the actual experiment showed it wasn't actually appear only that part.
In what frequency band?
Yeah, we used the frequency. We used the 4 to 120 hertz because we use this because the gamma wave hasn't been investigated in this stage because it contains some artifact, muscle artifact. So we just open the room for the future investigation. But in this experiment, we use the wavelength. So it, as you may already know, it represents a low frequency band or high frequency band. And every single participant, every single trial, the node of the wavelength is always different. So we can't actually say which frequency band can be used in this experiment.
Any other question?
How can you prevent that users don't make motor imagery?
So your question is,
Yeah,
do we
you
still?
don't need motor imagery.
Yeah, we don't need motor imagery because if you imagine that if you are using motor imagery, I found that some participants they feel difficult to using imagination of moving your hands or moving your feet. So rather than motor imagery, vocalization is much more intuitive to all the participants. So that's why we choose some kind of some covert sound production instead of motor imagery. So we don't use that.
More question? So I guess we move on to the next speaker. Thank you again. Our next speaker is